Just about these things. Measure this DC motor means that this guy is a DC motor, but this guy does not have any brushes. So we talk about the brushed DC motor, and we know that the brush is not just one single brush. We might have multiple brushes. The brushes and the commutator. And what is the functionality of the brushes and the commutator? Can somebody remind me? Why we have brushes and the commutator?
To transfer the electricity from the outside of the motor to the commutator?
No. The commutator and the brushes, the function of brushes and the commutator is that we change the current direction in the wire, in the coil, such that we have continuous output torque, right? If we do not change the current direction, the coil, the output shaft will be vibrating this way. No, so in comparison, the brushless DC, we do not have brush, but here, and how can we change the direction of the current? So that is, we need to pay more attention to this. So here today's objectives, we want to learn the basic construction of the brushless DC motor and learn how a brushless DC motor operates and the differences between sensor and sensorless. This is the commutation. You can see here, because we do not have brush, we do not have commutator, but we must have a way to change the current direction at appropriate distance. And how can we do that? We use a sensor, or another approach is that we use a sensorless commutator to do the commutation. How can we do that? So this is what we are going to learn. So next one, understand the differences between the delta and the star welding of configuration. For this brushless, we have two welding configurations. One is a delta just like this is a triangle, and one is a Y. Y is just very intuitive, just like this letter Y. And finally, we understand the difference between brushless DC motor and brushed DC motor, and how they are different, and what conditions we should use this, and what conditions we should use that another one. So for comparison, here I'm also talk about this is for comparison. I put this is a permanent brushed permanent magnet and brushed DC motor here, and we can see, we can recall, and for this brushed DC motor, we have permanent magnet, and we have the spring, we have the bunch of brushes circumferentially, and we have this commutator. And so these two guys, and these 1, 2, 3, the brushes and the commutator, and they accomplish the goal of changing the current directions at appropriate time in order to obtain the continuous output torque. And we also have output shaft, and so this is the coils here, the coils, and so this is the spring to make sure. So this is the brushes, they are in contact with the commutator all the time. So this is the configuration of brushed DC motor, and we have talked about last time. Right? For comparison, for the brushless DC motor, you can see for the brushless DC motor, just like inside out. So you can hear. So here is a DC, here is a magnet NY, okay? I'm sorry, N and S, North Pole and South Pole. And so this is a permanent magnet. And here, for the brushed DC, the permanent magnet is on the outside. But here, the permanent magnet is inside. Just as I said, it's inside out. So on the outside, we have these coils. We have these coils. This coil, you can see here, okay, C and C. they are connected. So if they have the same same labels, that means they are connected. So this is we call this a C pole C, polar C. Okay, this is called polar C, and we call pole C, POLE, pole C. So this is C minus and C plus. So here is a capital C, the capital C. These are two capital C's are the same. That means so this guy and this guy physically they are connected. You understand? So same thing for the pole B. Pole B, you can see B minus, B plus, and this is lowercase b, lowercase b. That means so these two poles and B and B, they are physically connected. The same thing for the pole A plus, A minus. You can see for this one, the coils are on outside, magnet is inside. It is totally different from this one. Questions so far? So we can see the poles determines phases. We call these the phases. So we have phase A, phase B, and phase C. So that one is a 3-phase motor. And there's a concept, stator. Stator means that something does not move. And we have a rotor. Rotor means that something is rotating. Questions? No questions? No questions? Hey, Kevin.
Which one do you prefer to work with, brushed or brushless motors?
Yeah, we'll talk about this later. Okay.
I'll talk about that.
Yeah. We'll compare.
Okay.
So because the brushes can cause a lot of trouble, and we will talk about this one later. You can imagine because the brushes, when this is the shaft is rotating, the brushes they are in contact with the commutator. What will happen? A lot of noise, right? Friction. If there's a friction, and they will generate the unnecessary heat. That means the efficiency going low, more noisy, and also sometimes there is the sparkles between these brushes and the commutator because they are contacting each other. And these sparkles, these spark can sometimes be dangerous. That's a very good question. We'll talk about this one later. So here, so we talk about these 3 phases, and here is how we just weld them. So physically, they are arranged so that they are offset from one another by 60 degrees. Electrically, so physically and electrically, the coils are arranged in one of the 2 possible arrangements below. So first one is Y configuration, and you can see if you tilt here, you had a little bit. So this is just like a capital Y, right? Do you agree? Or just look at this way. This is the capital Y. And you can see A plus. This is the common and A, common and B, B plus, common and C. All of them, they are connected together and then go to the ground. So this is the Y connection. And so second configuration is kind of different. It's just like a triangle, not just like a triangle. This is a triangle. You can see A plus, C plus, B plus. So here is A minus, B minus, and C minus. So here is common and A, common and B, and common and C. So this is 2 different configurations. So as I said, because in the brushless DC motor, we do not have the commutator and we do not have brushes, and there must be another approach to changing the current direction in order to maintain the continuous, to get the continuous, the output torque. How can we do that? Here, in order to perform the switching of the current direction in the coil, at the correct time, appropriate time, and otherwise the coil, the output torque will be rotating this way. To produce smooth rotation, we need to know something about the position of the rotor relative to the coils in the stator. And we should know the position. So incorporating a position sensor into the motor. So this is the first approach, and they call the sensor. We call censored commutation. Censored commutation means that a commutation with a sensor or sensors. So this is the first one. Whenever one of the Hall effect sensors, we talk about the Hall effect sensors. So this guy can record the angle and how much angle and you have rotate. So these are Hall effect sensors. So usually this sensor is a little bit bigger. It's triggered by the commutation mechanism, the corresponding stator coil, and will be activated. So here is the Hall effect sensor. So this guy is used to keep track of the angular position of your shaft at the appropriate time. And so this guy will send something, and then the computer, the system will know at this point I need to change the current direction. Or otherwise, and the output torque will be rotating this way. So this is one thing, right? So Hall effect sensors. When we talk about the sensors, when you learn the sensors, we have learned this sensor, Hall effect sensor, to measure the angular positions. So here just for to recall, to refresh you guys' memory, I just put this is the this diagram here again, right? We talk about this diagram when we talk about the brushed DC motor. You guys still remember? Okay. So I will ask you guys to use your own words to tell me how this can work, either in the quiz 1 or in the exam 1. Some students came here late today. Next week we will have our exam 1. So after our exam 1, we will start to learn the PLC. That means 1/3 of our semester is gone. Have flags, right? So I just want to show you for this is a brushed DC motor and how we accomplish. This is the current change. And for this is mechanical cycle for this one. Okay, for this one, this is without loss of generality. And for this is Y configuration and how they change the direction of the current. You can see mechanical cycle we call one complete revolution of the rotor. So this is a mechanical cycle. Electrical cycle and the sequence of all 6 stages, during which stage 1 pair of the leads is excited. And you can see, for example, the first electrical cycle, and the current will go from A plus and through this is the common point and go to the B plus. So this is how it goes for the first cycle. On the second cycle, it also goes A plus, but this time go to the C plus. And the third one is from B plus to the C plus, and fourth one is from B plus and to the A plus. So you can see this is the 6 electrical cycles can make sure that we will have continuous output torque. We will have continuous output torque. That means you need to change the current direction based on the electrical cycle, the 6 electrical cycle. When you program, and you need to do that, you need to change the cycle. You need to change the current direction based on this cycle. Otherwise, you cannot accomplish continuous output torque. You understand, guys? So how can I do that? Usually we have a microcontroller, and this microcontroller detects the position of the sensor, and then based on the position of the sensor, for example, the Hall effect sensor, and then this is the microcontroller will change the current direction, and that goes through in this is the motor. Okay. Are you okay? Are you following me? Yeah, here this for any mechatronic system, you must have a microcontroller first. That is the the head of our human being, that is the CPU. Right? Sensors and to put information to the head, and then the head process this information and then take some actions. So sensors here, Hall infrared sensor just tell us the position of the angular position of this is shaft, and then based on the shaft the position, and this is the microcontroller, and will determine whether it is time to change the current direction or not. And what is the criteria? Just based on this using these cycles, every 60 degrees. Are you guys okay? So one rotation has 360, right? Do you guys agree? One rotation we have 360. For this is 6 cycles, and that's based on the angular position of the shaft. You need to change the current direction. How to do that? Program and tell the microcontroller, and let the microcontroller to execute your instructions. Are you following me, guys? Okay, good. So you can see here on previously the previous example we have 3 phases, but now we can have multiple phases here. We can use more electromagnetic poles, resulting in smooth rotation and with less torque ripple, and requires that the drive electronics cycle through the 6 stages of electrical cycle multiple times to complete the revolution of the motor shaft. So definitely this one has some advantages, also have disadvantages. And disadvantages means that expenses, the expenses will be very, very high. And advantages means that the current, the torque, and will be will be more smooth, be smoother. Right? But you need to pay more money. It depending upon what kind of the torque profile you want, and also what is your budget. Definitely more money always get better service and better products. Do you guys agree? But sometimes it's not necessary. Otherwise, you just waste a lot of money. Okay. So the basic operation of the motor requires that we sequence and through energizing the coil, as I said, okay, the 6 cycles, and for which cycle you need to energize at what time, you need to know. And in order to pull the rotor along and sustain the rotation, and to change the direction of the rotation, and we need to reverse the sequence in which we energize the coil. So as I said, the DC motor, how can we change the direction of the rotational direction of the DC motor? You need to change the direction of the current going through the DC motor to change the rotation direction of this guy. The mode you choose depends on whether or not the motor includes the position sensing. We have position sensing. Sometimes we do not have position sensing. So second is a second commutation. This is what I just told you guys. So number of poles on the commutation mechanism and the mounting location of the Hall effect sensors are such that each of these 3 sensors is active for 180 electrical degree, and sensors are offset from one another by 60 electrical degree. So I'm talking about the 3-phase. This is a 3-phase DC motor, right? 3-phase DC motor, and we have 6 cycles. Each cycle they are 60 degree apart from one another. And how to accomplish the continuous output torque for each cycle, and you need to change the current direction based on the figure I just showed you. Right? Okay, so here, and how to do that, you can see the same thing. And you need to sensor A, sensor B, sensor C, and 3 sensors. And so how to, this is the welding, and how to just energize this is the coils. And you need to follow these 1, 2, 3, 4, 5, 6. For six cycles, and you need to follow this. And how to follow, and you need to program. What? You need to program and add this program in the microcontroller and let the microcontroller and to execute your instructions. The output of 3 sensors can be logically combined to determine which of the welding pairs should be energized and in which polarity. This one is positive, negative, or this one is negative, this is positive. I know, guys, you are doing senior design now, right? Which group or groups are building, designing some mechatronic systems? Are there any groups? No? What are you doing now? What kind of projects are you working on now? Have you decided yet, or are you still doing literature review or contacting the companies?
So we've decided on projects, but it has to be a thermal project.
Thermal project?
Yeah.
Only thermal, no electrical?
There will be probably electrical in the thermal, but
Okay.
It's split into 2 semesters for us, so we'll do thermal the first semester, and next semester we'll do mechanical systems.
You will do 2 systems?
yeah.
Oh, who is teaching, by the way?
Thetis, yes.
Professor Alexander.
Alexander, okay. Alexander, I know Alexander, I don't know. Yeah, so Alexander has another name, and because I don't know how to pronounce correctly. Okay, thank you guys. Thank you for the information. You can see, we just talked about the sensor commutation. The most commonly sensors use this sensor commutation is Hall effect sensor. But sometimes we do not use sensors at all. And then how can we do that? And we use back EMF. So because I'm old guys, can somebody tell me what is a EMF? Aiden,
Electromotive forces,
what is the unit? This is a Pascal, this is Newton, huh?
volts.
Yeah, good. Okay, that's good. I give you track, you just step out of the track. Good, thank you very much. That means the perfect understanding. So now this time we use the back electromotive force. Electromotive force is misleading. This is called force, but this guy actually is a voltage. Right? I told you guys, all the motor is a generator. Also, all the generators, they are a motor. Just like one coil, right? A coil have 2 sides. Do you guys agree? One coil have 2 sides, just like electrical, magnetic, they are always together. Whenever you have a motor, and then this motor is also a generator. And you have a generator, when this guy runs, this guy looks like a motor. So they use, because when this guy rotates, and they have back EMF, it's a back EMF, this guy's magnitude and is determined by the direction and by the position. Based on this, and and the regular angular position of this is a rotor, and then at this is appropriate time, appropriate instance, and you can change the current direction. So we have 2 configurations. One is a Y, and one is another one is a star. For different different configurations, we have different the drive, the circuits. And for this Y, and how can we drive it? And we can see, and we use this kind of the driving system. You can see here, for example, this A plus, and we have A plus, A minus, and we have the ground here. And so what is this one, guys? Can someone tell me what is this symbol? Clayton?
I don't remember.
What this one? Harry?
Transistor.
Yeah, transistor. Yes. Yeah, both of them are transistors. And what do we call this guy and what do we call this guy? Let's go. You want to say something, right?
Is it
Yeah. I know what I'm going to say. Yeah, say.
is it PNP?
Yeah,
Position?
PNP.
Okay.
What this one?
NPN?
Yeah. What? Remember guys, right? So this is a transistor. The Harry is very right. Right? Thank you, Harry. So NPN, NPNP, thank you, Jessica. You can see, okay, so whenever you see this kind of symbol, we know this guy is a transistor. And how can we differentiate them, whether this guy is NPN or PNP? Based on my learning experience, because I have been a student for a long time, you can see here, so when this emitter goes outside, arrow goes outside, going down. So this is a NPN. For the PNP, it is contrary, okay? It is opposite. For the PNP, so this is the emitter goes in, but also the emitter is on up, is in up position. But this one is lower, this is below, but this is up. Right? So this one we also call the staking. You know staking, right? Staking? You know staking, right? So when we take a shower, guys, all the water going down to the hole, that is called staking. However, the water coming from this faucet, we call the sourcing. Sourcing is going out, right? This is give us the water. So just like this one is sourcing, and this one is staking. You understand? This is one way I memorize these things, but you might have the better ways. How it works, guys? How it works? It works this way. And for this is NPN, this is a PNP. And for this guy, if the voltage difference between the base terminal and this emitter terminal is greater than a threshold value, and then I can have this current here. But similarly, for the PNP, if the voltage difference between the base terminal and also emitter terminal, but now this time it is this upper one. If this is a voltage difference is bigger than the threshold value, and so I can have current here. You have sense? And how it works, guys? Let me see how it works. For example, here, just give you one example. So here is a current. How can I make sure this current can go from this sourcing, is positive, and going this way? How can I accomplish this goal? And how can I do that? I can just make sure. So this is a NPN transistor work, and this NPN transistor work. If I can make these two guys work together, I can make sure that the current can go through this route. Do you guys agree? However, if I want to change the current direction within this coil and this coil, that means when this guy going down this way, how can I do that? I can just make sure this NPN works and also make sure until this guy is working. So then I can have this current. Right? So same thing for other poles. You can see there are some observations by changing which pair of half bridge, and we can call half bridge because this is the half bridge. The whole bridge is that we have a line here and we have motor here, and then we have transistor, another transistor. This is called whole H. But here, this guy is called the half H bridge, and half H bridge, as well as which is sourcing and is stating, you know, sourcing PNP, stating NPN. We can drive current in both directions and through each of these welding phase. And so this produces the maximum torque output from the motor at the expenses of high voltage required to drive the phases in series and a higher inductance of the series of coils. So keep in mind, so this one generates the best maximum torque. However, you need to spend more money. Why? You are using more transistors. So this is still the Y configuration, but now at this time we want to reduce the expenses, and then we do not use the half bridge two transistors. Now this time we only use the one transistor. So all these three the NPN transistors, and this is common, and this is sourcing. Common is the source. This is a positive. This is a positive voltage. But all other guys, we have ground here and NPN transition. And you can see, for this configuration, for this driving system, we save three transistors, right? But this guy will give you the lower torque. If this can accomplish your goals, it's okay. However, if you want to have higher torque, and you need to use the previous one, which requires the 6 transistors. You understand, guys? Always more money and give you better service. So here's the delta. We come back to delta. For the delta and the delta configuration, and now this time the first option is that we also have 3. This is the half bridges, and these are 3 half bridge, and so the delta drives using a pair of half bridge to drive one coil at a time. It has higher no load speed and higher stall torque. It requires higher current to produce the same torque output. So this is the features. Okay. In the example one, I might ask you guys use your common language, use your own language to tell me how many configurations we have for the brushless DC. How to drive them? What are the drive systems we have? What are the benefits? And this is the limitations. Okay. Okay, guys. Let me ask you a question. What is a no load speed and what is a high stall torque? Ready?
So no load speed is when the motor isn't pushing anything. So it is when its rotational speed is the fastest, but it produces no torque at that speed. And then high stall torque is basically the opposite. It is the minimum, or it's the point where you will get the highest torque in a system at its lowest moving speed, and it basically is just enough to overcome the stall torque movement.
Yeah. Thank you. Ready. So no load speed means the speed we have when there is no load. That means we do not drive anything for this motor. That is no load speed. No load speed is always the highest speed you can have for this motor. And the stall torque means the highest torque that when the speeding speed equals 0. So this is always at the very beginning of the rotation of your output shaft. At that instant, the spinning speed equals 0. But at that time, the stall torque is the highest one, right? So that's a stall torque. So comparison. So under what condition we should use this, and what condition we should use that? So you can see brushless DC motor. Brushless DC motor is quiet acoustically. Right? Why? Because there's no brushes. If no brushes, and then there is a friction, no contact between the brushes and the commutator. Whenever you have some two guys, they are contacting each other, or one guy is rotating, definitely you will have some noise. Do you guys agree? No matter how sophisticated the manufacturing level is, and you still have some. So as a result, the brushless DC motor, because there is no the brushes and no contact between brushes and the commutator, and no friction, and then this guy is quiet acoustically. And also this guy is quiet electrically. Electrically means what? And there is no arcing as the brush and the commutator interface. So when these two guys are rotating, sometimes we have sparks here. Have you guys ever heard of sparks? Sparks usually give us a very, very loud noise. And also it's very dangerous. It is safer. Brushless DC is safer, more reliable, and more efficient. The much higher maximum speeds and much easier to cool. Why? Why it is much easier to cool, guys? May I ask a question? Because the coils, they are on outside, right? The permanent magnet is rotating, but this guy is in the center. This is the coils, they are on the outside. The outside is much easier for the heat to dissipate to the outside environment. Much easier to cool. And then some people might ask, why we still use the brushed DC motor? Okay.
I don't know, like, seems like they're less complex and probably less expensive, so they're better for like maybe smaller projects or something.
Yeah, that's right. Right. So the major reason, I will not say the only reason, the major reason that this is a brushed DC motor still popular and still used very commonly is that this guy is much cheaper. But this guy is much cheaper. You can see, you can compare on how we control the current direction. And for the brushed DC motor, we do not need to have the sensors there, right? Or we do not need to measure the back EMF, and we do not need to just change the current based on what I see, what I just show you. How can I change the motor direction? And we need to program and give this program and to the microcontroller to determine at what appropriate instance, and you must change the current direction. Right? But here, for the commutator, for the brushed DC motor, and this one can be done automatically. Because you already have brushes and also commutator. So this guy can give you a very, very good function to make sure the current can be changed at the appropriate time. So this is dependent upon, and once you buy the commutator, okay, the commutator in the brushed DC motor and also the brushes, and when you buy this brushed DC motor, that is, you have everything, and you can control the current direction automatically. You do not need to program. You do not need to tell, this is the system at what instance you need to change the current direction. Questions so far? So this is, you can see on the BLDC, and it has a lot of advantages. As I said, the major reason and the brushed DC is still being used is that it is much cheaper because the system is less complex.